Hello, bonjour, welcome everybody, welcome to this session. So what we're going to discuss about today is the IoT technologies in Eclipse and how they can help you building products. I will use the smart home use case, but actually you'll see in the end that it applies to many other areas and businesses. What you take over from this presentation, hopefully at the end, is that Eclipse IoT Technologies are here to help. There are a lot of them, and you can use them to increase your productivity into building your products. I mean, real products, not just prototypes. Little introduction about me. I'm Laurent Lagosanto. I am now a senior architect at MicroEJ. I've spent since 1998 my time doing Java in embedded systems in companies like Gemalto, Dassault, and I spent a few years also in Oracle in the Java team. What is MicroEJ? MicroEJ is a technology, is a secure software platform that enables application developers and customers to write Java applications and run them on embedded devices. And by embedded devices, I really mean small constrained devices, devices that typically cannot run complex and huge software stacks like Linux. So I'm not talking about Raspberry Pis or these kind of devices. I'm talking about devices that run from a microcontroller, which means they cannot run complex stacks like Linux. We've been around since 2004. The first technology development started at this time. We are an independent software vendor. We're a French company, and what we build, the offer of MicroEJ is about the MicroEJ runtime environment, which is basically a Java execution environment for applications for these small devices, and also development tools like MicroEJ Studio or MicroEJ SDK that allows you to write these applications and simulate them on your PC or send them to actual devices or connected to your machine or even on the field. We have a small R&D team in France, in Nantes, but we also have offices in Europe and also in the US and in, sorry, in Asia. As I said, we've been around since 2004. We raised $5 million money, but we totally invested 20 million in R&D since we started. So some of our customers, as you can check, they are in many different business areas, from wearables, from automotive, of course, home automation, but also energy management or communications. And those are real customers that trust us. We also have a good level of industrial partnership at every level, because we typically behave as an integrator. So we deal with the hardware, with porting our software to the hardware, and then distribution of this hardware, and then we do some customer services with sometimes third-party companies, and we integrate some third-party software as well. For example, the Wolf SSL stack, or we run on top of some RTOSes like MicroEJ, and we have good partnership with these companies. And of course, since we do devices that are typically connected to cloud services, we have a good level of partnership with cloud providers. If I'm here today, it's of course because MicroEJ is a member of the Eclipse IoT work group. So if you don't know what it is, Eclipse IoT it's an ecosystem of companies that work together to build IoT technologies, Eclipse IoT technologies, based on open technologies, and that are available for everyone to use in actual product for IoT or embedded devices. There are three big names from the steering committee, but there are many other companies involved in the IoT, and each one of them is providing technology for the Eclipse IoT community. And since there are many companies, there are many projects, from MQTT servers to protocol stacks to cloud libraries, firmware updates, MQTT client, OSGI stacks, you name it. I mean, there's plenty of them. There are some of them that do not have a logo, but that's the type of scope that you get when you enter the Eclipse IoT community. It can be overwhelming, right? It can be too much to swallow in the first place, but there's a lot of areas that are covered by those technologies. And that's why in late 2016, the Eclipse IoT Working Group has issued a white paper trying to segment the verticals of the IoT, so to clarify which project goes into which area of the IoT. So at the center, I mean the geographical center of it, there is the gateway space, where you have devices running gateway stacks that are doing the bridge between the sensors and actuators and the cloud services. So these devices are pretty powerful. They have a good level of connectivity, whether it's Ethernet, GSM or wireless, Wi-Fi. They can run complex software stacks. Typically they run Linux, and on top of Linux they run a Java SE embedded version, and on top of that they run an OSGI stack, right? So, and they can be remotely managed and dynamically updated on the field. Some of them can even do some local processing. They have enough power that they can start to process the data that they collect before sending it to the cloud services. On the even smaller side, there is what we call the constrained devices. So these devices are the one that we at MicroEJ we target. These devices are typically made out of microcontroller-based boards, which means they reason in terms of kilobytes, sometimes megabytes when we're lucky. They reason in terms of megahertz, not gigahertz. And the software stack that we can run on these devices are typically made of real-time operating system, not necessarily because of the real-time part, mostly because of the footprint part. I mean, we cannot afford Linux on these devices, and anyway, Linux wouldn't run on these devices because there is no MMU available on the microprocessor, on the microcontrollers. So it's a much more limited software stack that we can run on these devices. But anyway, that's one of the areas that is covered by the Eclipse IoT community. And completely, of course, on the other side, there is the cloud platform. All these software stacks that runs on data centers typically, and that do all the analytics, the event management, the collecting of data, aggregation of data, processing of data, everything that is related to device management, backends, code management, anything you can imagine on the cloud side, on the backend side, and that's typically what the gateway is connected to. So if you want to get more details about this, you can check out the Eclipse IoT Whitepaper that was written by the committee, and that is available since the end of last year. So I've decided to go for a smart home use case. Why and why? Because of what's in a smart home use case. And typically there is one or more gateways. At least one of them is connected to the internet and providing us access to the network and to the cloud. And some other gateways, they may just be applicative gateways. For example, and you can think of an alarm system, the alarm central unit, you can think of it as a gateway, or the multimedia system, you can think of it as a gateway, or the heating system sometimes is also a gateway. So you can have many gateways in the device, and they directly access to the internet, or through another gateway, through a connectivity gateway, they access to the internet. And typically in a smart home deployment, in a smart home scenarios, there are also many devices in the house that are directly connected to the gateways or directly connected to the internet, and those devices, they fit into the constrained devices area, because there are many of them, so the cost is important. You cannot afford the same price as a gateway for a switch, or for a bulb, or for a temperature sensor, of course. So you have to build these devices with cheap microcontrollers, cheap systems, right? You have to issue them in volumes. You can tell that for one gateway there might be 10 or 20 devices connected to it, so the price, of course, is important. So, some of these devices, they have UIs. They can have some LCD screens. Some of them have touch screens. Some of them are they just have buttons and LEDs. And there are some devices that are just headless and that are just sensors, like temperature sensors or door opening detectors or window opening detectors. And all those devices, in some way, they can interact and they can participate into the IoT software stack that is deployed throughout the house. And of course, the constrained devices, typically they interact with some hardware, like what we call the temperature sensor. The temperature device is actually made of a microcontroller controlling through GPIO or through I2C a physical temperature sensor, and the microcontroller is running a little software stack, publishing information to the gateway. And of course, in a smart home scenario, there is typically a backend service. There is typically a cloud management system. Nowadays, everyone wants to do some management through their mobile phones, so there needs to have some cloud services available accessible from out of the home. And you can check that the Eclipse IoT technologies, from what I've said before, they cover the whole spectrum. So the idea is that using only the Eclipse IoT technologies, you can build a complete infrastructure that will work in a real use case, in a real deployment. So where does MicroEJ fit in this? MicroEJ is a complete Java stack, a complete software stack, that is running a Java execution engine for applications written in Java to be executed on microcontrollers. So I'm not talking about running Java on the PC or running Java on a Raspberry Pi. I'm really talking about running Java applications on devices that have less than a megabyte of RAM, that can have 128K of RAM, for example. So we have a complete stack that goes from the target hardware, typically based on a Cortex M0 or a Cortex M4 or Cortex M7 for the most powerful devices. Then on top of that, we have the BSP for those birds, and then we put our execution engine here, and then we have the memory management with an automatic garbage collector. We have the schedulers, because the platform is multi-threaded. We have the component management, because we can dynamically load components, we can dynamically load applications. It's not just pre-flashed, and it's not a monolithic firmware. It can be updated on the fly, and you can download application to the device. So for that, you need a component management system. And there are language features like the strings and everything related to text and everything related to I/O. And on top of that, we have the file management, the storage management, the I/O stacks, TCP/IP and the socket APIs and TLS. And even on top of that, we also have the MicroEJ framework for doing graphical user interfaces. And for devices that have cloud access, we also have libraries like HTTP and REST libraries that allows us to get access to the MicroEJ store. So the applications can be downloaded directly from the device to the board itself. So again, we target constrained devices, and we think in terms of kilobytes or sometimes megabytes, but not in terms of gigabytes or gigahertz, right? So of course, it's not the full Java you will find on Raspberry Pi. We don't have the whole set of APIs. We don't have the full Monty, as they say, but at least we have enough to run HTTP requests and to run, you'll see, some quite complex software stacks. So clearly on the IoT spectrum that I've defined before, we're on the constrained device part. We made a contribution last year to Eclipse in the Eclipse Edge project. So Edge and the J is not a typo, it's a hint, right? J is for Java in this case. So we define a Java API for these kind of constrained devices. So what we open source is the API and an implementation of this API for MicroEJ enabled devices. We're looking for an implementation of this on a Raspberry Pi 2, because we know that many people have Raspberry Pis and they don't necessarily have microcontrollers handy, but for the moment it's only available on top of MicroEJ. And what we deal in the Eclipse Edge project, what we deal with is about APIs for communication, because for a constrained device it's mostly about communication. So the objective of Edge is to define APIs to access GPIOs, to access CAN buses, I2C buses, SPI, anything related to the local network that is formed by the hardware connectivity of the microcontrollers. We started open sourcing the GPIO part and the serial communication part, and we're working on the SPI and I2C stacks. There's been an event in the end of last year with Google. Google has unveiled Android things, and I mean, for everybody, it was a little moment of doubt, because okay, now there is an Android proposition for constrained devices that has GPIO, that has SPI, and all this. And we had our own moment of doubt with this, but then we looked at the spec and we looked at the APIs. I mean, it's huge from our perspective. It's still Android, it's still Linux, it's still on a Raspberry Pi, it still takes 40 seconds to boot. That's not what we target. The devices that we target, it's not the same scale, right? Typically our devices, they boot in 15 milliseconds. That's not 40 seconds, right? So we cannot afford those stacks. So we think there is a room for these kind of devices, and we think there is room for this kind of implementations in the market. So what we also define in Edge is what we call the ADC, the Edge Device Configuration. So what we took is the big Java SE implementation, and Oracle already did a job of reducing it to Java SE embedded. And Android has made its own fork of it, its own version of it, and it's a subset plus a superset of other APIs. There is, of course, MicroEJ, which is even smaller and has its own subset. And we define EDC as the minimum part, the minimum common part. So the idea is not that you will write your applications against EDC, because, for example, you will not find an application framework in EDC, but at least you can write your libraries against EDC. And if you have a library that is built against EDC, then you're pretty sure that it will be able to run on MicroEJ, of course, but also on Android, also on Java SE embedded, or also on Java SE standard edition, Java SE. If you want to test it out, it's available. Since it's a MicroEJ implementation, you will need some MicroEJ tools, but they are available for free. I will not go into the details, so you'll have the slides anyway after that, but here's the procedure to test this on these boards. So in December last year, we unveiled the implementation for the STMicroelectronics F7 board. This month, we are doing an implementation also. We are releasing the implementation for this board. It's a Renesas board. It's typically the size of an Arduino connector with a microcontroller in it. That runs MicroEJ, and we also are making the last modifications for the implementation of the NXP LPC Expresso board, which is a little bit like the F7 board, the same type of board with a touch screen. So if you want to test it out, you have the GitHubs and everything, so you can test it. So that's what we contribute to the community, but actually, we are getting even more from the community, and that's the principle, right? We're getting a lot from the Eclipse IoT, from what is available. Not just the software stack, even the tools that we built, MicroEJ SDK and MicroEJ Studio are built out of Eclipse. We wouldn't be able to build our own IDEs, given the size we are, and we wouldn't be able to give them away for free if it wasn't for Eclipse, for the IDE, for the Eclipse IDE. So we're getting, just with that, we're getting a lot of benefits from the Eclipse community. But not only that, there are many existing projects in the IoT community that can run and that are already Edge compatible, and that's what I'm going to focus on for the next minutes. For example, Leshan, we use it for remotely managing devices. There is a client and there is a server, and we use both in our context. Californium is the protocol implementation of CoAP, the implementation of CoAP provided by the Eclipse community, and it's used in Leshan. Paho, which is an MQTT client. There are different MQTT clients, but one of them is written in Java, and you'll see that it can run on top of Edge and MicroEJ. Mosquito, of course, is very convenient. It's an open source implementation of an MQTT broker. So if you want to do MQTT deployments, MQTT tests, and you have devices, and you don't want to buy a server, or you don't want to build a complete infrastructure, then you can just do it with Mosquito. So starting with Californium, what did we do in actual products, in actual context with Californium? We started with a port of Californium for projects related to energy management. We had a European energy provider that asked for a fleet management system for devices that were in the houses. The devices were behind firewalls, so they could not be contacted directly, so we had to use a solution like CoAP to get access to the devices. And it worked pretty well out of the box. But you know, in our business, it's all about optimization and size. I mean, size matters. So what we did to Californium, we did a little fork of it, a little tweaks to it. Not much, actually. There is the thread management. We reduced a little bit the thread allocation because we cannot afford that much threads in our systems. And we little bit tweaked the timer management. And also we removed a sorting algorithms that was too big for our purpose. I mean, the team sort thing was like 4 kilobytes of code. In our context, we could not afford it. So that's the kind of figures that we are dealing with in our context. But it almost worked out of the box, as is, for a commercial product. Leshan, what did we do with Leshan? Actually, it was in the same context. We started with Leshan and Californium, and then the same energy provider asked for an even more constrained type of device in an even more constrained environment. So in this context, we could only afford a single TLS connection from the device to the backend. And we already had to have a TLS connection for MQTT, and we could not afford a second TLS connection on the device because you know, the cryptography algorithms involved and the buffer involved in TLS were too expensive for a device. So what we decided to do was to do our own specification and our own implementation of lightweight M2M, but instead of using CoAP, we decided to put it on top of MQTT and to rely on the already existing TLS connection to the MQTT server to multiplex the information into this channel. I know theoretically it's not the best scenario you can have, but the reality that we faced was that we can only afford a single TLS connection. So this was basically leading to this topology. Devices running Paho, publishing information to a Mosquito server that was connecting through MQTTS, of course, that was connecting to a Leshan server, and from that we could access the management console from Leshan, and for the firmware management, the Eclipse Oakbit server. Out of this work, we created a specification that is available in the ESR consortium as a proposal for everyone to comment and to implement. The ESR specifications are free. What we basically did in this specification is that we took the lightweight M2M stack specification and we made an alternate version of it, keeping the lightweight M2M semantics, keeping a part of CoAP for the message format, not for the transport part, but for really the way the messages are structured. And that was, of course, transported on top of MQTT over a TCP TLS, over TLS over TCP connection. We also published a reference implementation of this that you can access freely. We have a server up and running right now, leshan.microej.com, that uses this protocol. And from the community store from MicroEJ, you can download application on your board and test this protocol on this board. And I will quickly show you a demonstration of this. So this, interesting. Okay, right. This is the Leshan server that we have up and running at MicroEJ. I have two boards here. This one is an ST F7, and this one is a Renesas Peach. Both of them are just running the Leshan client. And you can check out that there are 3 boards there. So I guess someone at MicroEJ doesn't know that I'm doing a presentation now, and they are making some tests. So there is a 3rd board. Given the idea of the board, I can tell that it's an NXP board. So the NXP software stack is already running, as you can see. Anyway, so let's check out the ST device from here. So in this context, I'm running the board and my PC at the same place, but in a real context, the board would be somewhere, and the remote management console would be somewhere else, right? It's not, they do not need to be on the same network. That's the whole point. They typically are very, very far apart from each other. So from the Leshan management console, I can see the content of my board. I can read the content of this board, so you can see that it's running MicroEJ, and that it's an ST microelectronics device. You can check the version. It's not been released, it's a release candidate. And you can also do the software management of these devices. So you can see that there are applications running there. Those are system applications. And there is one of them. There is one of them which is the Leshan client. And then we have ThermoCloud. So ThermoCloud is a little mock-up application that is supposed to implement a thermostat application. So for now, we are just running the desktop application of the board. And if I activate ThermoCloud through the network, you see the application just started, and you have a thermostat that I can set the temperature I want for my heating system, right? Anyway, you cannot see it, but on the top right of the applications, it says that there is no cloud service. So there is a local application running a thermostat application, but there is no backend infrastructure that it is connected to. So if I continue in the list of applications here, there is the Eclipse IoT Free Data Hub. So that's an application that binds to the freely available Eclipse IoT MQTT server. That is a sandbox that is available for anyone to play with. I have an MQTT-FX client here that I can show you. And I'm connected to 2 topics here on the Eclipse IoT server, and there is nothing on these topics that is published as of now. If I go back to Leshan and I start the Eclipse IoT Free Data Hub connectivity, then on the background of this ThermoCloud application, you can see it's still running. This board will start connecting to the Eclipse IoT Data Hub and will start bridging the ThermoCloud application, sending its data to the MQTT topics. So if I go to MQTT-FX, we start seeing messages being published on the topic. So if I change the temperature, it's in Fahrenheit. Oh, sorry, it's in Fahrenheit anyway. But you can see published messages on the data hub. And I could also do the demonstration with the other board. It has a temperature publication system. It doesn't have a UI. There is no screen in there, but you can do the same kind of applications. Well, that's the type of things you can do. And remember, those applications, they are all written in Java, and they are all running in devices that have megabytes of RAM in this case, but this one is much smaller, actually. So that's about Leshan. Right. So what did we do with Paho? Well, obviously, we made it EDC compatible and Edge compatible. And we forked from Paho version 1.0.2, and the fork is freely available on the MicroEJ GitHub. We made no modification to the core, actually. We just added a new backend. We added a new backend to these two backends, actually, one for SSL and one for one without SSL in cases you have the need for SSL. Quickly on this, does it translate to actual products? Yes, it does. Here's the SOWI home station. That's an EDF product, Électricité de France product. This kind of product. It's been sold since the beginning of this year, and it's entirely based. Well, it's based on technologies that I've shown you today. There are many icons there on the device, and each one of these icons is actually a Java application running on the device. I cannot tell much about the device itself, about its content, but it's a Cortex M4 device, and it doesn't have megabytes of RAM. It has kilobytes of RAM. It has Wi-Fi connectivity, and it's connected to multiple cloud services. The typical use case is this one. You have a smart home scenario with a gas metering and electric metering system and the heating system. This is connected to the cloud, to the SOWI infrastructure by EDF. There is a mobile infrastructure that you can use to access your data from your mobile phone, typically leading to the traditional topology of the sensors, the gateway, and the cloud services. And the SOWI station is there in the middle for you to control your environment from your home, to control the heating systems and the sensors and the door systems and the window system and all this. This is quite amazing for me. This product didn't exist last year. EDF came to us in late April last year, and the production of the device started in September. So it was from the idea to the physical product, it was only 4 months. And it wouldn't have been possible without the MicroEJ technology, but it wouldn't have been possible without the Eclipse IoT technologies, right? And I think that's what you can take over from this presentation, is that with Eclipse IoT technologies, you can build actual products that do work, and in a very, very short period of time. Thank you for your attention.